Hey, what's up you guys? Yes, today I'm going to be talking about some interesting parts about WebAssembly, giving a high-level overview, and talking a little bit about some low-level stuff, but keeping it kind of high-level, and yeah, I hope you enjoy it. I'll also show a cool code demo at the end that you might enjoy. Before getting into WebAssembly, I want to talk about the web and why it's a really cool place to ship products. I mean, a lot of this is kind of obvious, but I just really want to hammer home this point. The web is extremely portable. I mean, if you send someone a link to your website, they can access it on pretty much any device. Their phone, their laptop, their smart TV. Like, it's very portable. You don't have to worry about what operating system it runs on. You know, for the most part, as long as it runs in a browser, you're pretty much good to go. Everyone knows how to use the web too, and it's extremely easy to share. You send someone a link and they click on it. Bam, they're at your website. But the web has been troubled and it's been missing something. We've been stuck with JavaScript, and I'm not gonna lie, I do love JavaScript, but it's got some issues. It's not as fast as like native code, native C code, Rust code, C++. Other lower level systems level programming languages are a lot faster. Porting apps to the web is kind of a pain. You build some accounting software back in the day that you run on Windows, and then now you want to put it on the web. It's kind of a pain. You'd have to, back in the days, maybe port this to JavaScript, rewrite some of the code base, and then you're potentially managing two different code bases with two different software teams. So you're putting a lot of money into that, and that's not great. Introducing WebAssembly. It's a portable assembly format where you can compile any code to Wasm and it'll run on the web. So any programming language, for the most part, at least a lot of the popular ones, will compile to WebAssembly, which is an assembly-like binary format that can execute code in the browser. And you don't have to worry about it compiling to different architectures or computers. It's all handled by the browser for you. So you compile to WebAssembly, ship that WebAssembly to a user, and in their browser, it will handle running it on an x86 machine, an ARM machine, and all of that. A number of programs that have existed before have been ported to the web using WebAssembly, and I think they're cool example use cases, and some that have been built with WebAssembly first in mind. The first thing I want to talk about is AutoCAD. This is a 40-year-old software. There's literally code in it from 1982 that's, I think, C++, and has been compiled to WebAssembly and now can run in the browser. Also, without AutoCAD, the speed of JavaScript, you'd be running into limitations where the C++ code base, you wouldn't. Photoshop, it's also been compiled to run in WebAssembly in the browser. Snapchat has a C++ video filter feature that is cross-platform. You have it on the browser as well as on the phone. This allows them to have one code base that works in multiple places. Figma was built with WebAssembly in mind. Its beautiful C++ UI was built to allow for very fast and fluid and comfortable movements to make something that you wouldn't otherwise be able to scale at a speed that feels comfortable in JavaScript. I'll also mention this Notes app. I forget the name, but it was in Google's I/O a couple weeks ago. They mentioned this. Imagine if you're an iOS developer making a note-taking app. You've been building this app for 10 years using Swift. It's on iOS, and you want to port it to the web or somewhere else. With Swift, you can compile it to WebAssembly and get some of the UIs also working in the browser to get a very beautiful port without having to re-engineer too much to get it working. Also mentioning Unity games. When you're publishing your game, you have an option to compile it to WebAssembly and run it in the browser. I should also mention there's a number of libraries that work great in WebAssembly. For instance, TensorFlow.js, which is just TensorFlow ported to JavaScript, runs great because the optimized C or whatever code C++ is compiled to WebAssembly and can run in the browser, which is very useful. Other libraries like that, you can imagine how WebAssembly can allow for benefits like that. So basically any programming language you want, with some caveats, in the web. And a very important part about WebAssembly is that it was designed with these 4 tenets in mind: safe, fast, portable, compact. With safety, WebAssembly was designed with a zero trust model where you don't have to trust the code that's executing on your computer. You know, typically when you're running code on your computer, you want to make sure you trust it. It's from a developer that you trust, something like that. You wouldn't want to just download some random guy's binaries, .exe file and start running that. You know, that's how you get viruses. But with WebAssembly, because it's sandboxed, the code can't like escape and do evil things in your computer. Just like how when you go on some random web page for maybe a sketchy website or really any website, you don't really have to worry about what the JavaScript's doing because it's sandboxed within the browser and it can't, I don't know, latch out and do too many evil things. WebAssembly is fast. It's near native speed, which is very important for getting that speed performance boosts that we saw in those previous applications. It's very portable. As a result, it works across browsers, any operating system, and such. Here's an interesting thing though. It was designed to be very compact. Because loading web page times are very important, you want to make sure that when you're loading a web page, it loads immediately and it's responsive and you can start running code without waiting too much. It was important for the size of the WebAssembly binaries to be very small. There's some other cool features that are involved with getting this speed to executing the code down as well. For instance, you can stream compile WebAssembly and run WebAssembly code while it's downloading. Similarly to how on YouTube, you can start watching a video before it's fully downloaded. I'm going to show a code demo. Here's just one piece of software that I wrote using WebAssembly recently for an image processing class. I'm just going to run the code. Got some warnings. And here's my application. It's called IMGPROBOX, and basically you can upload an image and apply image processing operations to it. So rotations, I don't know, grayscale, inverse, histogram equalization, as well as convolution. So interesting filters like, let's say a Gaussian blur. I'm not sure if this is picking up too well in the video, but this image is definitely a lot more blurred than this one. But there's also other interesting kernels you can apply, like a Laplacian or a Laplacian of Gaussian. And I'm just going to go over briefly the implementation for this and what this looked like in my code and how I'm running it in the browser. I will mention just before getting into this, there's very optimized ways to doing what I'm doing, and you can probably get similar speeds with JavaScript. But I hope that this can kind of give you an idea of how you can achieve faster speeds with WebAssembly and how it can be easier to write performant code in WebAssembly than it is in JavaScript. Keep in mind, JavaScript is fast, but it's harder to achieve the speed than it is on WebAssembly. Also, this specific algorithm that I'm going to be demonstrating can be sped up significantly using a more efficient version of it. But I'm just showing this again just as a demonstration. Okay, so imagine if I'm manipulating an image. Let's say I want to blur the image. There's a few ways to do that, but I'm going to specifically talk about a simple blurring technique where I look at the other pixels around it and I take the average. So when you think about it, all an image is a 2D array of colors. And these colors are represented by codes. A color image would be represented by, I guess, like 3 numbers, or maybe 4 if you add in transparency. That's where we get the RGB from. In this example here, I'm just doing a black and white image. There's only one value per, I guess, like square of this 2D matrix. And it represents a value between 0 to 255. 255 would be white, 0 would be black, let's say 128 would be gray. So let's say I'm going through this image and I'm calculating a blurred version of it. And I'm just going to choose this pixel as an example. So one way to do it is I could take and I'll show the example here, is I could get a 3x3, what's called a kernel, and then basically set all of these to 1 and normalize it, and you'll see this results in a blurred version of the original image. That probably doesn't make any sense, so I'm going to walk through the algorithm to explain what this matrix is doing. Just keep in mind a 3x3 matrix full of 1s. So if I'm blurring this pixel, for instance, and putting it into a new image, I'm going to look at the surrounding neighboring pixels. When I'm doing convolution, I'm going to be adding values from it together based on the multiplier of what numbers here. But they're all 1s, so just think of it as adding them together. 0 plus 10, 10 plus 15 is 25. 25 plus 20 is 45. 45 plus 0 is 45. 45 plus 15 is 60. 60 plus 30 is 90. 90 plus 0 is 90. So I get this value after adding these together. And then to calculate the blurred pixel version, I'm just going to take the average of that with all of these. So 90 divided by 9 is 10. So I would set this to 10 in my blurred version. And that's what's going on here. So this pixel here, let's say on the original image, is looking at the surrounding pixels and just taking the average and putting it here. I'll specifically say that normalize kind of divides these by 9. So in reality, this is really like a 0 point, this is really like a 0.1111 since it's 1 over 9. But let's look at the implementation for that. Just gonna zoom this code in a bit. So this is the convolve operation. And we're specifically just looking at this right here. So basically, what's going on here is I'm taking in an image, and this is written in Rust, which is, to put it simply, a 2D array of colors. And then I'm returning or I'm painting it onto an output image canvas. And I iterate through every single X and Y value in the image and set the pixel intensity to the sum of those values. So since it's normalized, it would be each of those pixels multiplied by 1 over 9, and then setting that pixel to that value. One tweet that I really want to show is by Solomon Hykes, the original creator of Docker. He said, if Wasm and Wassi existed in 2008, we wouldn't have needed to create Docker. That's how important it is. WebAssembly on the server is the future of computing. A standardized interface was the missing link. Let's hope Wassi is up to the task. So that's a pretty powerful statement. We wouldn't have needed to make Docker if WebAssembly existed? What does that mean for the future of server-side computing and how we initially used Docker, how we're using Docker today? And what does he mean by let's hope Wassi is up to the task? So far in the talk, I haven't introduced Wassi. It's the WebAssembly system interface that allows WebAssembly to talk to parts of the computer outside of the sandbox. So maybe, file I/O, network I/O, things like that. Wassi is a standard that's being built. I think it was announced in 2019, at least looking at this tweet, that allows for portable code to access parts of a computer, so that you don't have to worry about how a certain computer is implemented, if it's Windows or Mac or whatever. If you're running your code in Wasm and Wassi, it will work the same on different computers through this Wassi interface. And this could replace Docker for a few reasons. One of them is that WebAssembly is so compact. It's easier to transmit this stuff. It's a lot smaller. All right, I know what you're thinking. This sounds pretty familiar. Write once, run anywhere. Where have I heard that? Well, yeah, it is kind of similar to the JVM, Java bytecode kind of infrastructure for running Java. And this might lead you to think, why aren't we using JVM in the browser? There's a few reasons. WebAssembly was designed differently than JVM. First off, JVM was designed specifically for one language, Java. And although a number of languages now support it, Clojure, Kotlin, and even languages that were designed before it, like C, other languages like Python can run in JVM, it really was designed for Java. And it's also higher level than WebAssembly. There's more abstractions and such like that. And that also means there's more surface area for attack. WebAssembly is a lot smaller and has simpler instructions. The JVM also takes a longer time to start up than WebAssembly, and WebAssembly needs to start up fast to work in the browser. JVM does garbage collection and imposes many other specific ways of doing things, and it's strongly aimed towards a specific language, Java, like I mentioned, even if it can host other languages. Now, WebAssembly is getting support for garbage collection, but it's on the way, and it's done in a more portable way. Another part of running WebAssembly in the server that I want to talk about is running WebAssembly in Python. There's an open source project called Python Monkey that allows you to run JavaScript within Python and interoperate with Python and JavaScript objects. And this leads for a very good platform for using WebAssembly. So although you can compile code to run on your computer and execute it in Python, and a lot of great Python libraries do that, like NumPy. I think a lot of NumPy, I could mistake me if I'm wrong, was written in C, Fortran, C++. But WebAssembly could be an easier way to ship libraries using different languages, since you don't have to worry about portability or working on certain systems. Python Monkey is one way to do that. So essentially, you can load in WebAssembly using your typical JavaScript APIs for it and run code pretty simply. Another extremely exciting use case for WebAssembly is through distributed computing and edge computing. I'm specifically going to talk about a product called DCP. But before going into it, I will mention I do work for Distributive, which is the company that develops DCP. And I didn't ask for permission to talk about it. I'm not paid to talk about it. But there's probably some sort of conflict of interest. I just want to mention that. I am talking about it, though, just for the value that it adds to this talk on my own volition. But yeah, so basically DCP is a way of distributing workloads for compute, such as if you're doing research. Essentially, it turns any computer into a compute node that you can send stuff to be computed on. So if you're a university, you have a whole bunch of different computers, you could run kind of a worker on all of those. And if you had some grad student that needed to do some research, but maybe the supercomputer or whatever access isn't available, they could distribute it this way. And it's done using JavaScript and WebAssembly so that you don't have to trust the code that's running on your computer. This leads to some interesting opportunities because it creates a network for compute where you don't have to trust the work that's being done on your computer. You don't have to worry about how malicious it is like you normally would have to with these typical large distributed parallel computing projects. With this, anyone can submit a job that needs to be computed, and anyone can compute it without any fear. Finally, I want to talk a bit about WebAssembly's history. I think this gives some interesting context and helps you understand it a bit more. At least it did for me. First, I'll talk about Java applets. So interestingly, I think, I could be wrong, the main reason why JavaScript was created was to support Java applets, which allowed you to run Java in the web. Which, when you think about it, is pretty ahead of its time, maybe too ahead of its time. And JavaScript was supposed to act as the glue between the website and running the Java code in the browser. It didn't end up succeeding for a number of reasons, including security concerns, and I think licensing issues. Also mentioned Microsoft ActiveX, which was a way of, I think, running C++ code, or maybe C#, I'm not sure, something like that in the browser. This was very different than WebAssembly's like zero trust policy. Instead, this was a policy that involved code signing. So Microsoft would say, sure, this code is safe, you can run this. That doesn't really scale well, and there's a lot of security implications with that, and I haven't really seen ActiveX used much. Flash is probably a classic example. You've all loved to use Flash games. That was another way of kind of running code in the browser, but a bit more high level. I also want to talk about Chrome native client and Portable native client. This was a Google effort to make C, C++ work in the browser, kind of similarly to WebAssembly, but different in other ways. I kind of forget the details, but it was just one of the precursors that didn't end up succeeding. Yeah, and finally, I want to talk about asm.js, or assembly.js. This was probably the direct precursor to WebAssembly, and it involved compiling code like C, for instance, directly into JavaScript. But the JavaScript was a subset, a much faster and smaller, almost instruction-like looking type of JavaScript. There were issues with this. It's not as small as WebAssembly. It's not as fast as WebAssembly. Anyways, that's my talk on WebAssembly. I'll list my sources kind of in the description of this video. I hope you enjoyed it. And if you're curious about any parts of the talk, just let me know. I'd be happy to answer in the comment section. Thanks.